Hello, my name is Jonah Carlisle, and this is Image Denoising and Enhancement. So as an introduction, I just wanted to talk a little bit about image denoising and enhancement. So image denoising is, as it sounds, the removal of noise from an image, and that can be anything like motion blur, Gaussian blur, salt and pepper, dust on the lens, anything of that sort. Image enhancement is taking the qualities of an image that are either desirable or undesirable and increasing or decreasing those. That can be things like increasing the saturation of an image, increasing the brightness, lowering the brightness, things of that sort. So here's the goal of the project. We're given a number of sets of data with 6 different kinds of distortion. First, we have to create 3 of our own noisy sets of data. Then we have to create a pipeline of techniques and methods to address each of the 6 different types of distortions within our 6 sets of data. Then, using that pipeline, we have to use our techniques and methods to attempt to denoise and enhance a particularly bad blurry image. This is the data set that was given to us. Pictured are Brussels 3, Espresso Square, Wise on Rock Square, and the blurry image. The 3 on the left are the original images for their respective datasets. Each of these 3 also contains 6 different versions of each with a different type of noise applied to them. The image on the right is the challenging image that we must attempt to denoise. These 3 images make up my dataset. They are student parrot, student traffic, and student dandelion. I chose each of these images for their own specific reasons. I chose the parrot because it has a large amount of different colors, and also contains different lighting situations within one image. The feathers on the parrot, as well as the foliage, provide a lot of distinct edges that may prove useful in assessing the effectiveness of our chosen algorithms. The traffic image was chosen because it represents a highly relevant everyday situation in which computer vision may be used. Additionally, it has 3 different instances of text within the image, all at different distances from the camera. The dandelion image was chosen as something completely different from the previous 2. It's a close-up shot, meaning the field of view gives a notable blur at certain parts of the image by default. The hairs on the end of the dandelion also provide many thin lines, which may cause difficulties with certain types of noise. Now to discuss the different types of noise and how I chose to address them. The first type of noise was downsampling. When an image is downsampled, data is lost. That is completely unavoidable. As a result, when the image is returned to its normal size, there will be some notable amount of distortion. In an attempt to address this distortion, I both upsampled the image back to its regular size and applied a smoothing algorithm. This has caused the image to lose some notable amount of detail, but I chose this to be acceptable instead of the artifacting that was caused by only upsampling. The underexposure in the images was addressed by utilizing the Python imaging library's equalize method. This provides histogram equalization for the images and had a very notable effect. The only artifacting that was introduced as a result of the method was noticeable color banding within the image. This, however, is unavoidable, as the original image's color palette was crushed into a small range. Overexposure provides a very real challenge. In many of the images, there is hardly any detail left to be seen. Therefore, on images with a certain amount of detail left within the image, histogram equalization works just fine, as seen here. However, on some more problematic images, histogram equalization caused too much artifacting for it to be considered. As a result, on these more problematic images, an edge detecting algorithm was run in an attempt to bring out as much detail as possible from the image. Gaussian blur provided a pretty significant challenge. One method to address Gaussian blur is Wiener filtering. However, I was unable to achieve desirable results with the use of the filter. As a result, I instead just opted to use an unsharp mask to try and bring out as much detail as possible from the image. This worked fine for the first level of distortion, but the second level and beyond were hardly affected by the unsharp mask. As a result, it can definitely be said that Wiener filtering would be more desirable in this situation. The dirty lens noise was addressed by first applying an unsharp mask to accentuate the salt noise as much as possible. Then, a min filter was applied to remove as much of that salt noise as possible. As a result of the min filter, the image became quite dark. Afterwards, the image is brightened to offset this. The final result gives noticeable artifacting, but with the removal of much of the dirty lens from the image. Finally, the salt and pepper noise was addressed by first applying a median filter and then saturating the image. This is because applying the median filter by itself desaturated the image heavily. By applying this method, much detail was able to be retrieved from what was originally a problem image. Finally is the blurry image attempt. I say attempt because overall the results were not good. My attempts at Wiener deconvolution almost unanimously introduced more noise than they removed. I think this may be because the kernel I was using for the deconvolution of this image wasn't able to address for the curved nature of the motion blur, and as a result, often introduced more noise than it removed. Being unable to successfully apply Wiener deconvolution, I instead applied an unsharp mask in an attempt to sharpen the image as much as possible. As you can see, this did not change that much, and really did not affect the quality of the image whatsoever. The image in this case is only marginally sharper. This is likely because the image was not denoised before attempting to enhance it. There are a number of notable results from the objective measures of the trials. The methods used to treat downsampling actually increased the error across the board. This was expected as a result of the smoothing that was applied. However, the smoothing was applied for the sake of the subjective results, not the objective ones. While underexposure saw barely any change in MSE and PSNR, huge gains were seen in SSIM, summer, and unique measures. This is likely because these take into account structural changes. For overexposure, huge gains were only seen in the summer measure. This reflects summer specialty in measuring perceived quality. Once again, for applying the unsharp mask to the Gaussian blur in the student dandelion, the summer metric showed huge gains, indicating an increase in perceived quality. The same can be said of the dirty lens noise applied to the Brussels 3 image. A significant increase in the summer measure can be seen, whereas all of the other measures remain mostly unchanged. The salt and pepper noise in the student parrot image saw huge gains in each of the three measures that take into account structural changes. As for what can be improved in the methods, the number one answer has to be the use of Wiener deconvolution. In the case of the Gaussian blur noise and the blurry image, the unsharp mask that was applied is effectively a band-aid on a larger problem. The underlying noise has not been removed or addressed. As a result, Wiener deconvolution should be used to remove this noise. The effects of Wiener deconvolution can be seen on the right from the Wikipedia page on Wiener deconvolution. These effects would help significantly in the case of the Gaussian blur noise as well as the blurry image. One of the biggest takeaways I had from this project is that image denoising and enhancement is not an exact science. Once a type of noise has been applied to an image, it's impossible to return the image to its original state unless you know exactly what operation was performed on it. This is obviously impossible, so some amount of data is always lost when a distortion is applied to an image. Therefore, when denoising and enhancing, you will always have to make trade-offs. Removing one type of noise will always introduce some other type of noise in its place. The goal is to optimize that noise for the user's specific use case, whether that be subjective viewing or objective analysis. It's these trade-offs that make image denoising and enhancement such an interesting topic to work on.